In this video, we're going to be looking at the concept and properties of pendulum. What are we going to do? We're going to review what a pendulum is. We're going to define the term physical pendulum. We're also going to review what a simple harmonic oscillator is and some of its basic properties. We're going to relook at the forces that act on a pendulum. We're going to see how a pendulum can sometimes act like a simple harmonic oscillator and see why a pendulum sometimes does not act like a simple harmonic oscillator. We're going to calculate the instantaneous tangential acceleration of a pendulum, as well as calculate the centripetal acceleration of a pendulum. And we'll also apply that to finding the tension forces in the pendulum wire. We're also going to look at the factors that affect the frequency and period of a pendulum, as well as calculating that period and/or frequency. Why are we doing this? Because pendulums played a key role in our development of our understanding of the universe, and they are still used today as timing devices. Also, anything that swings on a wire or on a rod swinging back and forth actually models a pendulum. And while pendulums might seem like a very simple and obvious thing, there are still many commonly held misconceptions about how pendulums behave and act that causes a great amount of confusion for people, and then by analogy causes confusions on more complicated topics that we'll see later on. So let's review the basic forces that act on a pendulum. Basically, a pendulum is just an object that is hung by a string and swings back and forth. And there really only are two forces that act on the pendulum if we're ignoring air resistance, and that would be the force of gravity pulling straight down and the tension force that pulls along the wire. The force of gravity is the driving force that makes the pendulum swing, but if you notice, not all of the force of gravity is going to be pulling along the motion of the pendulum. Here we have the purple line illustrating the arc of the motion that the pendulum will travel. The force of gravity pulls straight down. This force is not parallel or perpendicular to the motion, but instead at some other angle, meaning that it will be broken into components. One tangent to the motion that will drive the pendulum, and one that will go along the radius, which will be fighting the tension force. Please notice that as the pendulum swings, the angle that the gravity force will be with the arc is going to change, which means these two component forces are going to always be changing their magnitudes as they pull on the pendulum bob. The bob being the little mass at the very bottom. So while gravity is in fact the driving force for the pendulum, not all of the force of gravity will be driving the pendulum. The tension force, if you notice, is perpendicular to the motion. This is going to have no impact on the actual speed of the pendulum as it swings. The tension force is solely responsible for changing the direction of the motion. Here we are going to see something that moves in an arc or semicircular fashion, so we will be looking at centripetal motion, and that's going to be the role that tension plays. Pendulums played a key role in inspiring Galileo to investigate the motion of falling objects. If you remember, we had discussed once before that Galileo had noticed that pendulums of the same length swung at the same time rate, going back and forth, regardless of their mass. It was believed at his time that heavier objects would fall faster than lighter objects, and so if that was true, heavier pendulums should swing faster than lighter pendulums, but his observations show that that was not the case, that from his perspective and from his experiments and observations, it seemed that only the length of a pendulum affected the time it took to swing back and forth. It was these observations about the motion of a pendulum that inspired Galileo to investigate the motion of objects that fall under the influence of gravity. One of the other experiments that he had developed was the U-shaped ramp, where an object would roll down a smoothed ramp across a smooth surface and then back up a smooth ramp on the other side. And when he did this, he noticed that the objects seemed to seek equal heights, which means whatever height you started the ball at on the first ramp, that would be the exact same height the ball would reach on the other side if the ramp was very smooth. He also noticed that if he had tilted the second ramp so it was at a less steep of an angle, the ball traveled not the same distance along the ramp. Here we have a short distance, here we have a much longer distance, but it would travel to the same height. So again, if this was 1.5 meters here, then the ball reaches a height of 1.5 meters over here. And no matter how shallow the angle, the ball would just travel a greater distance along that ramp till it reached that starting height, which then led to a thought experiment where he asked the simple question, if I was to roll something down a ramp and then across this flat, smooth surface that never went back up, since that ball never reaches the starting height, would it actually stop moving? And based on the observations that he had, the answer would be no. This laid the foundation work for Newton later on to develop his first law of motion, which is an object once set in motion does not change its motion in any way, not in speed nor direction, unless there is an unbalanced external force causing that motion to change. In short, the motion of an object never changes unless there's an external reason to make it change. This idea revolutionized how we viewed the universe, but it was based upon the work of Galileo, who was actually first investigating things because of the motion of a pendulum. Now, when we take a look at a pendulum, it does in fact swing from side to side, much like the ball on the very top ramp here, and it does seem to seek equal heights on both sides of the pendulum, and it never seems to stop. And so many people will actually try and apply Newton's first law of motion to this as an explanation, saying, well, the pendulum once set in motion will simply stay in motion. But that is not accurate. That is not the application of Newton's first law here. But if you notice, the pendulum is always changing direction of motion. It also speeds up on the way down and slows on the way up. Newton's first law of motion does not explain the motion of a pendulum or why it stops moving. There's a whole other concept that needs to be played. You need to be careful of this because if you shortcut Newton's first law to just say objects in motion tend to stay in motion, then that seems to apply to a pendulum on why it doesn't stop moving. And that's definitely not the case. Now, the reason why a pendulum does in fact seek equal heights on both sides of the swing and doesn't seem to stop swinging in the absence of air resistance comes from a concept that we're going to look at later on more in the course, known as work. Gravity pulls down on the bob on this section, causing it to speed up. At the same token, when the ball then is swinging up, gravity is going to pull down, doing equal amounts of work to slow the ball down and stop it. Once the ball then starts to go down, gravity does the exact same amount of work on the ball to speed it back up on the way down. But then the gravity on this side has to then do the same amount of work again to stop the ball from moving. Later on in the course, we're going to deal a lot more with the concept of work. You might remember from an earlier class that work is equal to force doing the work times the distance parallel to that force. If you don't remember that, that's okay. It's been a long time since you were in middle school and you may not remember this force equation, but we will be looking at this later on. But the key thing here is if gravity is going to be having the same amount of influence on one side versus the other, then to get the same amount of work done, the distance traveled has to be the same on both sides. And work relates to energy, and energy must be conserved. Again, a concept that hopefully you had seen in an earlier course. If not, or if you don't remember it, again, we're going to look at this much more in the future. But the bottom line is, right now we cannot use the concept of inertia to explain why a pendulum swings back and forth and just doesn't stop swinging. That's all going to stem from the concepts of work and energy.